We're going to program the encoder now. But first we create the pattern number array that contains our pattern nominators. We need that because the encoder already processes the information which pattern we are. Also we need to tell the function the current pattern. We initialize every variable of the array to an arbitrary number. The first data point gets on 0 though. The Z counter pointer captures the size of the memory block that the audio commands pointer points to. But first we set the data block of the audio commands pointer to a relatively large size so we can experiment with. Reminder, this tracker is still a beta version. In the future I want to implement dynamically reallocation of memory when it's needed. We set the first, respectively the 0th pattern to default values for the encoder to recognize the starting point. Error checking. We copy the content of our data stream starting from the current pattern to the end and overwrite everything starting from the current pattern with garbage values. All the stuff later gets written back into the data stream, but first we write new comments into the data stream, which is the entire purpose of the encoder. After the new commands are being added, we put everything back. Without copying everything, the new commands would just overwrite other content in the data stream, which would create a whole mess. This is the idea behind the sound commands after memory block that we're allocating here. At first we let our encoder walk through all potential patterns until we find the current pattern. The decision which one the current pattern is made by the number of the pattern nominator. So if we are, let's say, in the pattern with the number 6, this code block will count to the 6th pattern in our data stream. We're going to program the first part of our encoder now. These loops here walk through all columns and count how many empty cells between our commands are and write that information as time vector into our audio commands pointer data stream. Here you can see how we create the column counter. It's starting from 90. When we write nodes like C# into the pattern, the hash symbol or number sign will be recognized by the value 89. If we're building 0 vectors, the actual command value gets written into the stream. Remember the video I made about D and encoding. Reminder, not its ASCII value but a transformed value by the adding number 17. Please watch my video about encoding to understand what's going on here. We're approaching the second part of our encoder. From now on we write into our data stream which values our commands have, whose time vectors we've built a moment ago. Reminder that 0 vectors, respectively the values of those, are already written into the stream. We have reached the end. New commands are built, now we can copy the old content back. I made a few mistakes, let's correct them. Now let's see what it looks like. We put our first two commands into the pattern. Now let's interpret the results. In column 90 we have after 4 rows the first command. In column 92 after 4 rows the first command. Don't mind the minus 51. The encoder doesn't recognize these values. Now let's add another two commands. Our data stream is enhanced by 2 elements. Now after the first command the second command appears after 2 rows. This is for now the content of the entire pattern. Recognize how number 127 finishes the pattern. Let's add a command with time vector 0 now. The actual value, here 84 which is 67 or a C in ASCII and 70 which is 53 or number 5 in ASCII gets written next to the time vector values. After number 126 the value doesn't appear another time, that's how we save memory space. As you can see, there are only 4 numbers stored after 126, although it should be 6. Short addendum, I deleted the other keys to save some time, let's put them back. Let me explain the meaning behind the action counter. This variable adds the new commands into the C counter pointer. You know that guy that captures the size of the data stream with the audio commands pointer. By adding new commands, the memory needed will enhance. We proceed with our completion of the draw sound data function. Now we will create dependencies for the VRAM and audio commands pointer and vice versa. I will show you after we're finished that the VRAM gets data from the audio commands pointer while the audio commands pointer itself receives data from the VRAM within the encoder function we've already implemented. In this first loop we again check in which pattern we're currently in. Remember, this function draws the current data. Its task for now was reading data from the VRAM. Our job is now to decode the data from the audio commands pointer and send that data to the VRAM. This process seems to be useless since the VRAM already contains all data that it needs. But in future we want to switch patterns and the VRAM can't contain data of the entire song for memory reasons. It has to get these informations from the audio commands pointer. In the following loop we clear our data inside the VRAM. This will be the proof that the audio commands pointer will write data back into the VRAM. The value counter does kind of a complicated arithmetic operation. Remember, we need to assign time vector data before separator 126 to the actual command value beyond the separator 126. This assignation is done by the value counter. As I've already mentioned, this is a beta version. It's probably way easier to set up an algorithm to compress tracker files. I came to the conclusion that there is a simpler process like putting time vectors and values together, and time vectors could point directly to the position where commands are placed without walking through the columns and counting the empty space. But more about that in future videos. Here we decode and extract the data from the audio commands pointer. We transform the values back to the ASCII values and put the data into the VRAM. Reminder, the VRAM is still empty, respectively set to default value, and gets all its information here now. After we walk through one column, we process the next one. I hardly can show you what changed, since this process happens to be on the back end. Let us do following experiment. We want to put a node like C# on the screen. You know, that number sign symbol. When we build our 0 vector, we should get an output by the print function into the debugging console.